machine learning in the case when there are latent variables during training process. So mainly when talking about general framework of EM algorithm and its possible extensions. There's some examples. So first, please raise the hands those of you who know what is EM algorithm. Not too much. Okay, and who thinks that EM algorithm is mainly designed for separating the mixtures of Gaussians? Wow. Okay. Good. So the aim of my talk is to show that EM algorithm is a much more general concept, and the separation of mixture of Gaussians is just a tiny particular case of classification. So the algorithm is much more powerful. So during my today's talk, we'll start reviewing probabilistic modeling in modern machine learning, and this part will be complementary to the talk of Chris Bishop, which was the day before yesterday. Then we'll review Bayesian framework, Bayesian approach to probability theory, and its distinctions from a classical approach, from also known as pragmatist approach. Then we'll present exponential class distributions that are extremely useful for building these complex probabilistic models. Finally, consider learning with the latent variables and present a general form of EM algorithm, probably the end of today's part. And next time, we'll consider several examples of real-world models with discrete and continuous latent variables, and how EM algorithm can be adopted for learning these models. Then consider several interesting extensions of the EM algorithm, and finally conclude with the stochastic optimization and how this concept, which is extremely efficient in the case of big data, can be applied for in the EM framework. So first I will start, as many other speakers have started, on the question, what is machine learning? So it may seem funny, but just to ensure that we are on the same way, and to ensure necessary notation. So the machine learning covers now quite wide spectrum of different problems, so it's quite difficult to characterize it in unique terms. So this is my version. So from my point of view, machine learning tries to find hidden regularities within the data. And in classical formulation, data is just a set of objects, where each object is represented by vector variables. So a subset of these variables is called observed variables, and it is assumed that these variables can be measured for arbitrary object easily. And the subset of variables that characterize each object is called hidden variables, and these variables, well, it is assumed that they're very difficult to measure for a particular object. So we can afford only measuring for some limited set of objects. And this limited set is known as a training sample. So we'll denote observed variables as x, hidden variables as t, and training sample as x training to training. So for those objects, we know both observed and hidden variables, and the task is to find dependency between observed and hidden variables in such a way that when we give a new object for which we know only observed variable, we could easily predict the value of the distribution on the hidden variable. So probably this is the most general formulation of machine learning problems, because it covers classification, regression, clustering, reinforcement learning, and many other kinds of machine learning formulations. Although maybe there are some exotic formulations that are not covered by this definition. So our goal is to come up with some decision rule that is able to predict hidden variable according to observed variable or variables. And we do this by tuning the weights of our decision rule, the weights of our machine learning algorithm, and these weights will be known as W. So we will work with three groups of variables, x, t, and w. X are observed variables, t are hidden variables, and the w are the weights of decision rule. So this is all just a simple example I gave in order to be not so abstract. So very well known two-class classification problem. So here the feature space, the space of observed variables is real two-dimensional space. So X belongs to two-dimensional real space. The space of hidden components is just binary, so a chemical component may take one of two values. And here we apply a straight hyperplane model. The space of parameters W coefficients for linear combination of features plus vice. So the decision rule is just a sign of linear function computed on features and the weights. So just an example. Okay, now we'll try to review probabilistic formulation of machine learning problem, and in order to do so, we'll need to remind several known facts from probability theory. So from probabilistic point of view, the dependence between observed and hidden variables, I put it in terms of joint distribution. Joint distribution where hidden variables depend on observed variables. So in order to do so, we need to remind what is conditional distribution. So here's the definition. The conceptual form is following. So conditional distribution equals the relation of joint distribution divided by marginal distribution. Or a mathematical formula is so. If we are given joint distribution of x and y, if we divide it by marginal distribution on y, we'll get conditional distribution on x given y. And the two basic rules for working with probabilities, known as product rule and sum rule. So according to product rule, any joint distribution can always be represented as a product of one-dimensional conditional distribution. So for example, if we are given joint distribution on x, y, and z, we will always rewrite it as following. P of x given by z times P of y given z times P of z. Note that the condition is been reduced from item to item. From symmetry considerations, we may also write it as following: P of z given x, y times P of x given y times P of y, and so on. So any reorder will give us different decomposition on the one-dimensional conditional distribution. And second rule is the so-called sum rule that states how to obtain marginal distribution from a joint distribution. So if we are given joint distribution on x and y, and we would like to obtain unconditional or marginal distribution on y, all we need to do is just to integrate out or to marginalize with respect to x. So we take joint distribution and take perform integration with respect to unneeded variables. But now if we substitute as a joint distribution, we substitute its decomposition on one-dimensional conditional distributions, we get this expression. So the integration of P of y given x times P of x dx. But this integration immediately has a probabilistic interpretation, because note that it is equivalent to take a mathematical expectation with respect to x random variable. So it can be written as follows. So this is just weighted voting or weighted averaging of conditional distributions. So if we would like to obtain unconditional distribution on y, we may average with respect to all conditional distributions of y given x and perform averaging with respect to x. So these are basic rules. Probably, well, at least you're supposed to know those rules. Now we come to Bayesian framework. Not surprising that it is based on well-known Bayes theorem, which is here. So the core of Bayesian approach probably is the interpretation of randomness. According to Bayes, we may use the language of probabilistic distributions to include our ignorance or our uncertainty, like Chris told, in terms of distribution. Then Bayes' theorem states how our ignorance or our uncertainty changes when we observe some indirect characteristic of unknown parameter. So assume that we would like to estimate theta. We don't know the value of theta. We have some prior knowledge about theta, which we encode as a prior distribution of theta. And then we observe some indirect characteristic of theta. So some variable that is somehow related to theta, which is of our interest. So we observe so-called the value of y, and this is a likelihood term that shows how likely, how probable is the given value of y if theta took the fixed value. And the Bayes theorem states how our ignorance changes. So we start from prior distribution and we come to posterior distribution. So posterior distribution is our ignorance after we have observed y. And this is exact equation. So actually, not the complex, but no, this is, I think, even greater. Such simple equation allows us to transform our knowledge from prior to posterior. And in the denominator, there's a normalization constant. Pay attention that it does not depend on theta, and it is here only to ensure that the left-hand part is a progressive distribution. So the integral of this posterior distribution with respect to theta should equal to 1. To ensure this, we need to put here normalization constant, and it is known as evidence. So, what is one of the benefits of working with the joint distributions? Anyway, if we know how to compute joint distribution, we may, at least in theory, compute any kind of prediction, any kind of conditional distribution. So, assume that we have a joint distribution over 3 groups of variables. One is u, that are variables of interest. We do not know their values, but we would like to estimate or to predict it. Second group of variables is our observed data, so we know the values of O. And there's also a third group of variables that I know it as L. These variables are unknown and are not of our interest, so we do not care of its particular values. So the question is, if we know how to compute the joint distribution, and how to compute this conditional distribution that actually contains information about prediction of U given O. And about it's not difficult, we just use the definition of conditional distribution and then apply some rule. So we take joint distribution and marginalize out with respect to unneeded variables. In the numerator, the unneeded variable is L, so we get here joint distribution of U and O. And in the denominator, we need to get distribution over O, so we marginalize with respect to L and U. So at least in theory, this is possible. This means that if we know joint distribution, we may compute any kinds of conditional distribution. So now let us consider what are the distinctions between classical approach to probability theory, also known as frequentist approach, and the Bayesian approach. As I thought, the main distinction is interpretation of randomness. And all other lines here in the table are just all consequences of the first, the main distinction. So here's the phrases are quite philosophical. So from a pragmatist point of view, randomness is something that is objectively indefinite. And from Bayesian point of view, randomness is just imposed our subjective ignorance. Let me give you a couple of examples. Consider probably the most classical random value, tossing coin. I think that everybody agrees that this should be an etymology of random variable. But let us try to consider it in a bit more detail. When we toss a coin, I actually know that a coin completely obeys the laws of classical mechanics. So if we knew the force with which we toss a coin, if we knew the tension coefficient, the coefficient of air resistance, the angular acceleration, and so on, actually we could predict the result, either until the head or tail, with 100% accuracy. The only reason we can't predict it is because we do not know some factors that define fully deterministic process of tossing coin. So from this point of view, it appears that actually we deal with the deterministic process, but some factors that define this deterministic process are unknown for us. And that is why we cannot predict the result of this deterministic process. Another example that shows that actually this ignorance is subjective. Assume that I come to bus station and look at the timetable and see that the bus arrives at 7:30. I know that we're in Russia, we're not in Germany, so our buses do not have the timetables to accurately. So the bus may come 10 minutes earlier, 10 minutes later. So this means that from my point of view, the time of bus arrival is a random variable. And I may include the ignorance about the arrival time in terms of suppose that, say, such a logical output, my PhD student, also comes to bus station, but he has a Yandex Transport application on his smartphone. So, do you know Yandex Transport? So that it shows the location of bus. So he opens this application, he looks at the bus location, and may estimate the arrival time with much more accuracy than he. The problem is that Yandex Transport still makes mistakes. So he cannot predict the exact arrival time. So he has, again, some uncertainty about bus arrival, but this uncertainty is much less than my answer. Because well, he monitors the progress, he monitors the approximate location of bus. So he may encode his ignorance, again, as a probabilistic distribution, but probably this distribution will have less variance than my probabilistic distribution. This means that we are both uncertain, but we are uncertain in different ways. So my uncertainty is encoded as one distribution, some uncertainty is encoded as a different distribution, although on the same domain. And now, if we think a bit more, we'll realize surprisingly that almost all random variables, almost all values that we call random variables, are actually deterministic variables. So they're actually defined by deterministic processes with some unknown factors. Some factors that are unknown for us. And they may be unknown for one person and may be known for another person. That is why this ignorance is subjective. So now the question, to those of you who haven't listened to my lectures before, can I give an example of a really random variable from a pragmatist point of view? So random variable where randomness is some objective indefiniteness and not a deterministic process. Yep.
Radiation decay.
Sorry?
Radiation decay.
Yep, right. At least according from a modern physics point of view. Maybe we will find something and it will appear that radiation decay is actually a deterministic process which is defined by blah blah blah. But from our present knowledge, yeah, this is completely random variable that cannot be predicted somehow. Any other examples?
Quantum mechanics.
Right, yeah. And it's famous Heisenberg indefiniteness relation. Good. Probably, well, at least our plan is stop here. Maybe the third example was Gibbs, but this is quite philosophical concept. Okay, now let us try to understand what are the consequences of this distinction in interpretation of randomness. So, variables. From pragmatist point of view, all variables are either random or deterministic. We may not know some deterministic values, but they are still deterministic. So, for example, if we try to estimate the parameters of a one-dimensional Gaussian, given sample from this distribution, we know that those parameters are deterministic. They are not random variables at all. From Bayesian point of view, everything is random, because randomness is just our ignorance. So even if we know the exact value of some variable, we may still encode it as a probabilistic distribution, but it will be degenerated, we will encode it as a delta function. All unknown variables can be treated as random variables. And this means that we may use the framework of probability theory to deal with unknown variables and to perform inference. Next, inference method. So inference is a process of determining the values of unknown variables given some indirect characteristics of those values. So from a classical point of view, the optimal inference method is a maximum likelihood method, which tries to get a quantity estimate of unknown variables. That estimate that has the highest value. And from a Bayesian point of view, the inference method is a Bayes theorem. So which instead of quantity estimate comes up with a posterior distribution. So we start from prior distribution, which encodes our ignorance, and we end with a posterior distribution, which still encodes our ignorance, but hopefully has less variance because we have built some information about our unknown variables. So the estimates in the classical approach are mainly point estimates, and they are usually maximum likelihood estimate, while in the Bayesian approach, the estimates are, well, at least in theory, should be posterior distribution, but sometimes we still need to get a point estimate. We usually take MAP estimate, so the maximum of posterior distribution, or the mode of posterior distribution. It appears that although maximum likelihood value is known to be optimal, and there are many theorems of classical statistics that show that maximum likelihood estimates are the best ones, the best ones that one can imagine. Unfortunately, all those guarantees, after the case when n goes to infinity. So the classical approach, the frequentist approach, is theoretically sound only when the samples are very, very large. To the contrary, the Bayesian approach may work with any size of our sample, even when the size of sample equals to 0. So if n equals to 0, we may still apply Bayesian approach. But in this case, our posterior distribution will be exactly our prior distribution. So even if our n says, if our sample size says 1, this already provides us with some information about unknown variable. Although the application of maximum likelihood approaches will quite severe also in this case. One may object that in the age of big data, these are not so serious constraints. But actually, it's not exactly so. Because when our samples are large, we usually tend to use more complex probabilistic models which involve more and more parameters to be tuned. For example, in modern neural networks, in very deep neural networks, the number of parameters is about 100 million. The parameters that we try to tune over the data. And in this case, actually these methods tend to overfit. And we need to perform some kind of regularization of our parameters. So now let us consider how this Bayesian approach works for machine learning problems. So in machine learning, there are two stages, well, roughly speaking. Training stage and testing stage or inference stage. On training stage, we are given training sample, X-train and T-train, and we would like to estimate W. Those W that we will use later on an inference stage to make prediction. So from Bayesian point of view, we just apply Bayes theorem and come up with posterior distribution of W. So we're not using point estimate. Ideally, we would like to use the whole posterior distribution here. So on the whole, it's computed quite straightforwardly, at least in theory. Of course, in practice, it's much more difficult because we need to take this integral, and that is rarely the case when it can be computed analytically. Pay attention that here I decomposed joint distribution of a likelihood and prior distribution of W, and this prior distribution can serve as a regularization term to prevent overfitting. So we restrict our W to tune completely to the data by rho, assigning some prior distribution. And again, this is the case even for very large training sets, because when we have very large training sets, we usually have a very high dimensional space of parameters W, and we still need to regularize them somehow to prevent overfitting. And on the inference stage, we are given a new sample of objects for which we know only X, only observed variables. And we would like to predict the hidden variables T. So in theory, we need to estimate these distributions. So P of T given X, and including the fact that we have observed training sample for which we knew X train and T train. So actually, we would like to estimate this distribution. And this is done by this equation. So actually, this is just weighted averaging of different decision rules of different algorithms for different W's with the weights proportional to posterior distribution of this W given the training set. So this term is obtained from a training procedure, and this is just all the weights with which we average in the space of all possible decision rules. So this is how we should deal if we are complete Bayesian. One of the advantages of Bayesian framework that probably made it so popular nowadays is the possibility of combining different probabilistic models and of building very complex models from simple ones using the life as a building block. So probably this can be illustrated by this well-known tale about several wisdomers who tried to touch elephant with different pieces and tried to make some conclusion on the animal that they touched, that they examined. So from this tale, the wisdomers could not come to any conclusion because probably they do not study Bayesian methods in the universities. But if they did, then probably there would be no problem. Why? All wisdomers know that they will examine some animal. So they have, of course, prior knowledge about possible, say, let us assume that they would like to estimate the weight of animal. So they know all of them have a prior distribution of possible weights of animals, because we know that the lightest animals still have weight more than 0, and the heaviest animal is probably a blue whale that has a weight of 33 tons. But again, no animal on our planet has a larger weight than a blue whale. So this information can be employed as a distribution in the space of weights. Now comes the first wisdom, touches a tail of elephant. So in the story, the wisdom concluded that the animal was a snake. Here he touched the tail. Probably he concludes that at least something like a snake. So, he may perform Bayesian inference to come from his prior distribution over possible weights of animal to posterior distribution, given the information he obtained from touching the tail. So he comes up with posterior distribution that probably has a peak in some low values. And now comes the second wisdom. He needs to combine his feelings with the information obtained from the first wisdom. So what does he do? Instead of using the initial prior distribution, he starts using in his Bayesian equation, he starts using posterior distribution obtained from the first wisdom. So he takes this posterior distribution as his new prior and performs Bayesian inference and computes his posterior distribution, which already encodes two pieces of information. Not only his information, but also information obtained from the first wisdom. Then comes third wisdomer, who takes as his new prior the posterior obtained from the second wisdom, and so on. So after performing an examination, probably they will have a quite accurate estimate of weight of an elephant. And this is the conceptual form of how different probabilistic models that may deal with completely different and non-intersecting sets of observed variables can be united in one complex probabilistic model. So now this simplified version of Bayesian learning, probably many of you have met this version. This is MMP learning. So if we are not able to estimate exactly this posterior distribution, and if we recall that to estimate it in the exact manner we need to perform this integral here, that may not be practical. So instead of doing this, we may approximate our posterior distribution with a just point estimate, with a delta function. And of course, it's quite reasonable to assume that this delta function should be centered at the maximum value of our posterior distribution. So to do this, we only need to maximize our posterior distribution, and which is equivalent to maximize numerator in our Bayes equation with respect to W. This is much more simple task than the task of performing the exact posterior distribution. And we found argmax WMP in contrast to maximum likelihood estimate that we usually denote as WML, and that is argmax of just the likelihood term, ignoring the prior distribution. So if we found this WMP, then the inference is also quite simple, because here we substitute, instead of exact posterior distribution, we substitute just a delta function, and the integral vanishes, and we come up with this quite simple equation. So instead of performing weighted everything, we just take the most probable decision with the most probable values WMP. So now let's consider the second part of my talk, the exponential class of distributions. In English literature, sometimes it's referred as exponential tabular distributions, but I would like to stress, and I would like to use some class of distributions to stress that this is not parametric family of distributions. This is functional class of distribution. It is not defined by parameters. It has a much general form. So this, the distribution or the parametric family of distributions u y given theta belongs to exponential class. It can be expressed as follows. So here f of y is arbitrary non-negative function. G of theta is a normalization constant, which ensures that the right-hand expression is a very probabilistic distribution with respect to y. So the should be equal to this integral. And the only term that unites both theta and y is this exponent. So the exponent under which there is a linear function with respect to theta. So this is a linear combination of theta times uy. Some functions referred to as sufficient statistics. Why they're called sufficient statistics? Because actually they contain all the information that is necessary for estimating theta according to the sample from this distribution. So assume that we're trying to solve our main problem of mathematical statistics. So we're given probabilistic distribution which is known up to parameters, and we observe some sample generated from this distribution. And our task is to perform estimation on theta. So to do this, actually, we don't need to keep the sample from this distribution. All we need to keep is just the sum of these sufficient statistics. So assume that, say we're trying to estimate the parameters of one-dimensional Gaussian, so the mean and variance, and we're given 3 random objects that are coming one by one. So actually, we don't need to keep all of them in memory. All we need to keep is just the sum of sufficient statistics on this sample. So if next object comes to us, we update our sufficient statistic and remove the object, clear memory, and be prepared for another object. So this is quite good property, and it is especially useful when we need to deal with large samples. So now let's consider another attractive property of exponential class of distributions, the property of logarithmic normalization constant. So let us consider the derivative of log of g of theta with respect to theta g. So the derivative of log is just 1 divided by g of theta, and now the derivative of g of theta with respect to theta g. So we recall that g of theta is our normalization constant, so it is this integral. Now we substitute our derivative inside of the integral and perform differentiation and obtain this equation. So the derivative of exponent is still exponent, and the derivative of linear function is uj of y. But here, this is exactly p of y given theta. So these two terms and this denominator. So this is our initial probabilistic distribution, and this means that actually our derivative, our partial derivative, is exactly equal to the mathematical expectation of J's sufficient statistics. So this is quite good, because generally speaking, if we would like to estimate the mean of some function, we need to perform such kind of integration. That can be difficult, the integral cannot be, sometimes can be computed analytically. But in case of exponential class of distributions, all we need to do is just perform differentiation of our normalization, of log of our normalization cost. And we immediately get the expectation of sufficient statistics. So no need for integration. Well, by using the same method, we may estimate the second derivative, and not surprisingly that it equals to covariance between i's and j's sufficient statistics. But what does it mean? That the Hessian of log of j of theta is a covariance matrix, and we know that covariance matrix is symmetric and is positive semi-definite. This immediately means that our function log of j of theta is convex, right? Because for convex function, the Hessians are positive semi-definite. Now let us consider the log of our distribution, log of p of y given theta. So the first term is linear function, we'll consider this function as a function of theta. So assume that y is known and theta is unknown variable. So the first term is just linear function with respect to theta. The last term doesn't depend on theta at all. This is just a constant. And the second term is minus log of j of theta. If log of j of theta was convex function, then minus log of j of theta is concave function. Concave function plus linear function is still concave function. So this means that if we are given some distribution from exponential class of distributions, its logarithm will be concave. This means that maximum likelihood estimation is extremely efficient. Even if we do not know the explicit equations for the point of maximum, we may always find it using iterative methods for convex optimization. Maximization of a concave function is very easy in very high dimensional spaces. So the good news is that all discrete distributions belong to exponential class of distributions. Also, many table distributions, many distributions that you may find in Wikipedia, if you type probability distributions, also belong to exponential class of distributions. So these are some examples: Gaussian distribution, Laplace, gamma, beta, Dmitry distribution, beta distribution, and the chi-square distribution, and many others. But of course, not all distributions belong to exponential class. So probably any examples of distribution that doesn't belong to exponential class?
A mixture of distribution.
A mixture of distributions from exponential class.
For example.
Yeah. This mixture will most likely not belong to exponential class. Of course, there are some exceptions, but in general case, it is so. Right. So, for example, the mixture of two Gaussians. The mixture of two Gaussians doesn't belong to exponential class. This means that maximum likelihood estimation for parameters when we deal with mixtures of distribution is quite a non-trivial problem, because log likelihood function is normal concave. And just one example, let us show that one-dimensional Gaussian distribution really belongs to exponential class of distribution. So this is standard form, how we write down one-dimensional distribution. And from this form, it is not obvious that it belongs to exponential class of distributions. But if we write it as follows, if we denote minus 1 divided by 2 sigma squared as theta 1 and mu divided by sigma squared as theta 2, we may rewrite it as follows. And this is exactly the form of exponential class of distribution. Why so? Under exponent, we have a linear function with respect to parameters theta 1, theta 2. And consequently, x and the x squared are our sufficient statistics for one-dimensional Gaussian. This is normalization constant, so this is function g of theta. As a function f of x, this is just 1. No, that is still possible. So note that there is one-to-one correspondence between theta 1 and theta 2 and parameters which we usually use, mu and sigma. And these parameters theta 1 and theta 2 are usually referred to as the nature of parameters. So if we take logarithm of this function and differentiate it with respect to theta 1 and theta 2, we will obtain closed form expressions for expectation of x and the expectation of x squared. Now let us consider a bit more difficult problem. A problem when during training stage some of variables are not known for us. So let us assume that our likelihood p of x t given w belongs to an exponential class. And our prior is a log concave function with respect to w. So for example, as a prior distribution, we may use, say, Gaussian distribution that is log concave. Given u, the complete training set, so if we knew x train and t train, then we could estimate w and p easily, because this function is log concave with respect to w because it belongs to exponential class. And p of w is log concave by our assumption. Now let us assume that we know only x train and the t train is unknown for us. Then we need to estimate the maximum of this posterior distribution p of w given x train, not t train. This is equivalent, of course, to Argmax's log of w given x train. Then we may write down as follows, as a log of p extreme given w plus log of p of w. So this is just log of our prime, this is concave function, and the problem is with the first term. And it's no longer concave. Why so? Because it is actually the marginalization of complete likelihood with respect to t. So we need to take p of extreme t given w and integrate out with respect to all possible values of t. So the function under integral is log concave, but the logarithm of this integral is no longer a concave function. So probably it looks something like that. So it has many extrema, and it is not always how to optimize. This function sometimes is referred as incomplete likelihood, to stress that there are some variables in training sample that we do not know. That is why it is incomplete. This one, no. If we put extreme and train here, we will obtain complete likelihood. That is likelihood when the all training set is known. So, EM framework is a framework for optimizing such kind of functions. So functions that are not log concave in a quite efficient manner. So probably this is the last big equation that they all need. So let us examine logarithm of incomplete likelihood. So log of p of extreme given w. And let us perform several identical transformations. The first transformation. Let us multiply this incomplete likelihood by 1. We'll consider arbitrary distribution on t, q of t, and perform integration with respect to all possible values of t. Since q of t is a distribution, this integral will be 1. So we multiply our incomplete likelihood by 1, and then substitute, put log of incomplete likelihood inside the integral. Since this log doesn't depend on t, we may correctly do this. Our next step. Let us rewrite this incomplete likelihood as follows. So probably here, I'll write down an equation on the flip chart. So remember that our conditional distribution is defined as follows: as a German distribution divided by marginal distribution. Right? Can you see it? Good. So here we make use of this relation. We express marginal distribution as a relation of German distribution divided by conditional distribution. So in such a way. Pay attention that both numerator and denominator depend on A. But the derivation doesn't depend on A, because this is P of B. So this is what we did here. So here we go. German distribution divided by conditional distribution on T given extreme W. And this is exactly P of extreme given W. Next step. Let us multiply the function under logarithm by 1. Q of t divided by Q of t. Right? And now finally we split this logarithm into two parts. In the first part we unite German distribution and the Q of t in denominator. And in the second part we unite Q of t in numerator and the Q of t given extreme W in denominator. So first term is this one, second term is this one. So here we go. These are the terms. And let us have a closer look on these terms. So first the second term. What is this? This is exactly by definition a well-known Calvert-Lewin divergence. So observe the distance between two distributions. Okay, program. So remind you. So Canada divergence between two distributions Q and P is defined as an expectation with respect to Q of logarithm of relation Q of x divided by P of x. Yes. So this is Calvert-Lewin divergence. The good thing is that it is easy to show that this kind of divergence is always non-negative. And you may do it as an exercise. So it's always non-negative for any choice of probabilistic distribution. But pay attention that P and Q should be probabilistic distribution. And another good thing is that it is equal to 0 if and only if P of x equals to P of x. That is why it is sometimes called a tilde distance. And it's not a distance, it's not a method. Because, for example, it's not symmetrical. And the chi between Q and P doesn't equal chi between P and Q. But nevertheless, it is always non-negative and equals to 0 if and only if the distribution is concise. This is very good because if we realize that this is chi divergence, then we understand that the first term is OR bound for our incomplete log library. By the way, the question to the audience, why the first term is not chi divergence? Seems pretty much the same. The expectation with respect to some distribution and the logarithm of relation of the distributions. But it is not chi divergence. So actually, because these two distributions are defined over different domains. And the chi divergence is a divergence between two distributions that are defined over the same domain. So here's the numerator distribution with respect to x and t, and the denominator distribution with respect to only t. So this is not chi divergence, although it looks quite similar. So we now realize that L of Q W, so this is the first term, is OR bound. Actually, this is variation of OR bound, because it is OR bound for any choice of distribution P of t. It is always OR bound. And here we come up with some idea. Instead of maximizing this logarithm of incomplete log library, let us try to maximize this variation of our bound with respect to two parameters, to Q of t and with respect to W. Here we make use of another quite general trick. That is widely used in mathematics, not only in machine learning. The trick with establishing variation of our bounds. So assume that we need to optimize f of x with respect to x. And assume that this is extremely difficult problem, so we cannot optimize it directly. But if we are lucky to establish so-called variation of our bound function g of x psi, such that, first, f of x is always larger or equal than g of x psi for any x for any psi. This is the first property, and the second property is that for any x there exists, for any x0 there exists psi such that the bound becomes tight. So f of x0 is equal to g of x0 psi. So in this case, function g of x psi is called variation of our bound. And instead of directly maximizing f of x, we may iteratively maximize g of x psi with respect to x given psi with respect to psi given x. So we may perform this iterative process. Xn equals r max of g of x psi n minus 1, r max with respect to x, and psi n equals r max g of xn psi with respect to psi. And we may guarantee that this process is first monotonic, and second, it will always converge to stationary point of function f of x. So this is quite general trick in mathematics. It is used, for example, in many optimization methods. So this is exactly what we are going to do here. Pay attention that Q of t is a variational parameter. So actually our initial function doesn't depend on Q of t at all. When we start maximizing this power bound with respect to Q of t, we may realize that this sum doesn't depend on Q of t. This means that maximization of the first term with respect to Q of t is equivalent to minimization of the second term by Q of t. And this is good news because Q of t is a distribution, is a function. We cannot perform optimization in the space of functions in general case. Only in several few exceptions. And this is one of those exceptions. Because we cannot maximize L with respect to Q of t, but we may easily minimize chiral divergence with respect to Q of t. Because we know that chiral divergence is always non-negative and equals to 0 if and only if the first argument equals the second argument. So then we know that the maximization of the first term with respect to Q of t corresponds to equating Q of t to this posterior distribution, to Q of t given extreme data. Okay, and what about maximization of this variational bound with respect to W? Let us consider this term. If we split this logarithm on two more parts, we'll understand that the second part will consist only on Q of t and will not depend on W. So the only thing that depends on W is the first term. So this is logarithm of Q of extreme t given W multiplied by Q of t dt. And what is it? The logarithm of this function is a concave function with respect to W. Remember that this distribution belongs to exponential class by our assumption. And what is this expectation? Actually, this is just a convex combination of different concave functions. Convex combination of concave functions is concave function. So this means that the maximization of this expression with respect to W is just convex programming problem. So here's concave function with respect to W, and it can be maximized in an efficient manner. So probably this is it. This is EM algorithm in the general case. So on each step, we maximize our bound with respect to Q, given fixed value of W. Since it is equivalent to minimization of chiral divergence, we may write down explicit equation for Q of t. So this is just Q of t given extreme and given the current values of W. So after we have updated Q of t, now we update variational bound with respect to W, given Q of t fixed. So this is argmax of variational bound, argmax of this integral. Then we split logarithm into two parts and disregard the second part because it doesn't depend on W. So we obtain something like this. And this is taking the mathematical expectation, and any taking mathematical expectation is a convex combination. And this is concave function. So convex combination of concave function is concave function. So this means that finding the argmax of W is quite an easy problem, because this is a convex programming problem. This can be performed efficiently even if we do not know the explicit expression for argmax. We can always use numerical methods to get it. And the good news is that this variational bound monotonically increases. So probably this is geometric illustration. So we do have a log of our incomplete likelihood. So this is multimodal, not concave function. We start from some initial approximation. So we fix W to some arbitrary value, W0, and construct a variational bound that is tight in this point. This is the first thing. And the second thing is that it is concave. So we do this by performing each step and estimate Q1 of t. So we estimate Q1 of t in such a way that sets chiral divergence at the point W0 to 0. And this means that at this point, this lower bound will become tight. So now we have constructed lower bound, we may optimize it with respect to W. So this is it. Since this is concave function, the direct optimization is quite easy. So we have found argmax form, variation error bound, so we denote it as W1. This is M step. On M step, we update our W's. So after we update W to W1, we perform E step. So we recompute our bound. We update our Q distribution. So we compute Q2 of T in such a way that this variation error bound is tied to the point W1. And again, it is a concave function, so its maximum with respect to W can be found quite easily. So this is point W2. And so on. So the point W2 we will again update our Q distribution, we'll get another error bound, then we update W until convergence. And we can see that the process is really monotonic, and it will converge to some stationary point of this logarithm of incomplete likelihood. So probably this is, okay, we still have time. Let us consider the easiest possible example of application of M algorithm. This is a mixture of Gaussians or mixture of distributions. So this corresponds to the case when our variable T are discrete. So assume that T may take one of K values. Then our incomplete likelihood, so P of x given W, is a just marginalization with respect to T. And since T are discrete, our marginalization, so instead of integral, we have a summation here with respect to different values of T. So I wrote it down as follows. So P of x given the particular value of T, and the W times the probability that T equals K. And we sum over all possible values of T. And this is exactly a discrete mixture of distribution. So if each such distribution, if each component of our mixture belongs to exponential class, since second distribution is just discrete distribution always belongs to exponential class, then we realize that our complete likelihood, our complete probabilistic model P of x T given W belongs to exponential class of distribution. This means that we may perform M algorithm for estimating the parameters of each mixture component. So for example, you have a mixture of Gaussians, so the mixture itself is quite complex distribution, but it may separate from several simple distributions, and the parameters for each distribution can be estimated in an efficient manner. So probably this is again geometric interpretation. So assume that we have a mixture of two Gaussians. We start from some initial approximations, two Gaussians with arbitrary values of parameters. So first step, E step. For each object in our sample, we estimate the probability that it was generated from the first component or from the second component. And the probabilities here are encoded by Kautsky. So the more red is the point, the higher probability that it was generated from the red Gaussian. So this is E step. We have estimated the probabilities of latent variables. Now M step. On M step, we update the parameters of each of our Gaussian. Updated according to the weights of each point. So the blue points influence the blue Gaussian, the red points influence the red Gaussian. And we repeat the steps until convergence is achieved here after 20 iterations. So here's a formal description of our probabilistic model. So we see here that we do not use any kind of prior distribution on W. So our probabilistic model is just joint distribution on X and T given W. First, we assume that our objects in our sample are identically, independently identically distributed. So the distribution of the samples is a product of distributions of the separate objects. And we split this joint distribution according to product rule. So this is likelihood, P of x given Ti W times P of Ti given W. The first term is normal distribution with respect to xi, and the second term is discrete distribution with respect to T. So theta equals the probability that Ti takes particular value. So our parameters consist of, W consist of theta, mu k, and sigma k. And we may perform EM algorithm for estimating all these parameters in a quite efficient manner. Note that we could also establish prior distributions on W if needed. For example, we could say analyze two narrow gaussians because it's known that we may obtain infinitely large likelihood. We will place, say here, one of these two gaussians with zero variance in one of the objects. Then we'll have an infinitely large likelihood, but this, of course, solution that is not of our particular interest. So this is a degenerate solution. So we could establish POW in such a way that we penalize two narrow gaussians in order to avoid these uninteresting solutions. Okay, I think, yeah. And this is an algorithm for separating mixture gaussians. So this is again our heuristic model for mixtures of gaussians. The problem is to estimate W given only X. So we do not know T. If we knew T, the problem would be trivial. We will just estimate the parameters of each Gaussian independently. But if we do not know T, we have an incomplete likelihood. So we perform the EM algorithm. On each step, we estimate the distribution on hidden components, distribution on T. And since T encode, so T are here, they encode the index of particular component for each object. So in this step, we estimate the probability that object I was generated from, say, L component. And this is it. This is a quite familiar expression. Probably most of you already know. And on that step, we perform a weighted maximum likelihood estimation. So we update UK and sigma k as follows. So here we see that classical maximum likelihood approach would give us just the mean of xi's, and summation would be with respect to all objects that belong to component k. And here we sum all objects, all n objects plus the weights. And weights are proportional to the probability that ith object was generated from k component. And actually the same with the sigma k, although here I have misprint, I have missed this gamma, so we should do it was gamma multiplied here, gamma I of k. But oh, I think that's quite obvious. So these are equations that most of you are familiar with. The problem is that many people think that this is the algorithm in general. I guess that's so. This is just a tiny particular case of general concept of the framework. And the framework itself is much more powerful. We'll see on Monday other examples, not so trivial examples. Examples when I have continuous latent variables, examples when I have both continuous and discrete latent variables, and we'll see that using EM framework, we're able to build very complex probabilistic models. And finally, we'll see again on Monday that the understanding of the derivation of the EM algorithm allows us to perform multiple extensions. For the cases when direct application is not possible, but we may extend it, we may modify it in a correct manner in order to be able to perform approximate EM estimation. So this is possible only if you understand the derivation of the essence of the EM framework, and this was my name for today's lecture. So probably this is all for today. Thanks a lot. So I guess this.
Yes. So is there any interpretation of from y function?
Probably not. So the only requirement that f of y can be an arbitrary function. We only need that should be non-negative, because otherwise this will not be a distribution.
Because I saw in some places people call it base measure, and I wanted to understand recently what does it mean, and it just failed.
Very well. It is sometimes referred to as a base measure. Probably, well, I would suspect that this means that for some values of y, this function can be 0, and that's why it defines the base of distribution, the domain of distribution. You see? For example, we may imply that f of y, well, say, takes 0 values when y exceeds 1 and is less than 0. This means that we have defined the Bayesian distribution, and the distribution is from 0 to 1, because otherwise it will be 0. So probably this is the reason why f of y is called Bayesian measure.
Yeah. About the example with elephant. So in the story, the case was that every man was sure that he was holding the whole animal, right? So they were mistaken about not about the values, but about the distributions. So can this theory and mathematics describe the case when we're not sure about the distribution itself? So here you provided very concrete distributions, right? But they're maybe wrong.
Do I understand correctly that you mean, can we generalize this framework for the case when we don't know exactly our prior distribution?
We're not sure about the mistake of the measurement. Or the distribution itself. Distribution depends on the model, as I understand. But the error may go wrong.
Well, the answer is yes. Because in both cases that you mentioned are the examples of model selection problem. So when we fix the uncertainty, when we fix prior distribution, we will get one probabilistic model. If we are not sure about this uncertainty and about prior distribution, then we define different models, different probabilistic models. And then the question is how to perform model selection, which model to choose among the wide range of models. It can be 2 models, 3 models, it can be continuum of models.
I was thinking that the distribution itself might be a variable for English.
Sure. This is exactly what I mean. That actually you may go even further. You may establish distribution on distribution and optimize it in a Bayesian manner.
Have it been done?
Yeah.
Well, can you give an example of a system? Or
I can provide you an example of several methods where it was done. For example, for classification and regression problems, method known as relevance vector machine. Are you familiar with it? Yeah. This is an example of automatic model selection problem, where we are not sure about prior distribution. So we put prior distribution up to parameters, and we can establish prior over prior. Or we may just perform maximum likelihood estimation on the hyperparameters. But in both cases, this is exactly what you're speaking about. Thank you.
My question is where we need maximization of incomplete likelihood. It seems that in supervised learning we always have training set. We have both X training and T, the hidden parameters training. So why do we need incomplete likelihood, not complete? So what is the application of the EM algorithm?
So probably this is partly the topic of my Monday's lecture.
Okay.
But I will answer. So first of all, there's also unsupervised learning in machine learning, right? And in unsupervised learning, we do not know some parameters.
Yes.
So this is one area of application of AM-like methodology, but not the only one. Second, there's so-called weakly supervised learning. Assume that we're given training sample, we know X, but we don't know the exact values of T. We know only the subset of its possible values. This is now a very popular formulation. Why? Because obtaining fully reliable training set is quite time-consuming problem. For example, assume that we would like to train, say, image segmentation algorithm. So an algorithm that takes an image and segments it. So it returns class labels for each pixel. As a training set, we would like to see a set of images which are fully segmented. So can you imagine how much labor it's going to spend on segmenting, say, one image, 1000 by 1000 pixels? No, it's quite difficult to segment just one image. Now assume that you need to segment, say, 10,000 of images. You will shoot yourself before you finish the work. At the same time, we do have millions of images for which we do not know the full segmentation, but we know, say, the objects that are present on the image. We don't know their particular locations, we do not know their particular pixels, but we know that they do present, and some other objects they do not present. So this is actually quite a rich source of information. Unfortunately, it can be taken into account when we perform fully supervised learning. But if we perform, say, unsupervised, or this formulation is called weakly supervised learning, we may use AM framework or using these weaker level objects in our training procedure. And in case of big data, this is quite an often situation. Because large amounts of data are usually weaker labeled, they are not fully labeled.
Thank you.